Okay, so today we're going to talk about gain structure. So the interesting thing about gain structure is, boy, if you don't get this right, especially in the beginning of your signal flow, you will find yourselves with some real issues down the line as you get towards your processing in the middle, and then especially as you get to your output stages. You'll just find that you're having a hard time dialing a room in. The audio will either be too low to trigger dynamics, or it'll be too high and it's overdriving. The old saying is garbage in equals garbage out. So today we are really going to focus on how to make sure you are getting a really good signal coming in. The one caveat on this is that, if you're getting a bad input signal from whatever the source is, we're not going to magically be able to fix that. So we want to make sure that we're getting good sources, and then we're translating that into really good signals as we go through our audio path. All right. Why am I not? There we go. So proper gain structure is the key component to getting the best audio performance out of your Q-SYS system. I don't know that I can say that enough times. We get a lot of calls from people that are having trouble, especially when you start trying to do conference rooms and far end and AEC and things like that, that they just are not happy with the way it sounds. They don't like it. And 9 times out of 10, we can track that back to some sort of a gain structure issue. So let's talk a little bit about gain structure, about the language of audio, and some of the terms we're going to use as we go through some of these concepts. So the first thing we're going to talk about is the noise floor. This is the minimum amount of signal that you're going to see that is just being generated by the circuit. So on this graph on the right, you're showing that we have a negative 81 dBu noise floor. So in most professional audio devices, plus 24 dBu is the clipping point. And we talk about clipping when in the dynamic audio class, where once your input voltage is higher than the maximum voltage of the power supply, or if the incoming sine wave is larger than the input drive or device can process, then the excess sine wave or the excess voltage gets clipped off the end. That's why that's called clipping, is because it's actually clipping the high points out of the signal. You cannot pass a signal that's bigger than the power supply of the circuit that you're feeding. So that's your maximum level on most professional devices, is a plus 24 dBu standard clipping point. So we've got our noise floor, we've got our clipping point. Everything between that is what we call our dynamic range. This is the allowable signal range between the noise floor and our clipping. So when we start to, you'll notice that on this, it says greater than 105 dB is the dynamic range. The reason for that is we're considering negative 81 dBu to be the max of the noise floor. But if that noise floor actually drops down, negative 83 or negative 85, you would actually get a bigger dynamic range. So we typically just find the maximum value of the noise floor and then work backwards from there. So in this instance, we would have around 105 dB of dynamic range. So let's talk about headroom. Generally, it takes about a 10 dB increase in SPL for the listener to perceive a doubling of the perceived signal. And we like for our audio signals to have about 20 dB of headroom in the signal that we're reproducing. So we want to do 2 things. First of all is we want to make sure that we are significantly above the noise floor. So we want to look at our signal to noise ratio. We want to make sure that we have enough signal to sufficiently get above that noise floor. So the sweet spot in the middle where we're trying to hit, that's called our nominal level. This will allow us to have adequate headroom as well as maintaining our SNR. In professional audio, you're looking at a +4 dBu nominal line level. In consumer products, you're generally looking at about a -10 dBV nominal. And then mic level is actually, well, mic level can be anywhere from about -36 to about -60. And that there's really not a standard. So those can be kind of hard to nail down. But what we're going to talk about for these demonstrations and for these examples is we're going to talk about a professional line level signal coming in at +4 dBu. Okay. So let's talk about how DSPs get a signal in and then manipulate them once they're inside. So the preamp has some analog circuitry where gain is added to a signal so that we can match the level that we want to sample at the analog to digital converter. This all happens before we get into the digital domain. So what we have is a little analog preamp. Every DSP on the market has some sort of a little analog preamp. Once we get into the digital space, so once we get past that analog to digital converter, Q-SYS uses a floating point DSP, so everything is just relative. We can scale up, we can scale down, all of that. So that's why it's really critical to have a nice, clean signal when we hit that AD. So we want to make sure that we have our input level coming in. We're going to tweak it a little bit with that analog preamp, and then we're going to hit that AD converter with a very nice, clean, strong signal so that we will now have something nice to work with once we get inside of our digital domain. So when we hit that ADC, that analog to digital converter, digital audio systems, they come through and they sample the analog audio waveform. The sample value gets scaled down in comparison to the ADC supply voltage. And this now gives us a conversion into a new unit called DBFS. So that's our decibels full scale. So once we get inside the digital space, we now are operating in DBFS, which in this realm, 0 DBFS is the maximum level that can be sampled. So when we're dealing with our analog side, everything before the ADC, we're looking at a +24 dBu is our max clipping point. Once we get inside to the digital domain, then we start looking at a 0 DBFS being our clipping point. And since we have already decided that we want to try to give ourselves 20 dB of headroom, our new nominal level when we start to set our target levels is -20 DBFS. All right. So when we are trying to reach our nominal gain, we want to give ourselves that 20 dB of headroom on the input circuitry. So when you are looking at the mic line input on a Q-SYS system, whether this is from a QIO, whether this is a CIML from a 510, whether it's an onboard from an 8-flex or a 110, all of the mic line inputs present the same way. So you're going to be looking at, we've got our preamp gain, which you can see is highlighted down there. That's analog preamp gain. And then what you're going to see on the meter is DBFS. And if you've used other DSP platforms and you're used to doing that, then what you're going to do is you're going to sit down and you're going to say, okay, I need to give this thing preamp gain until I get to 0, because that's how I zero out a system coming in. What you're doing if you do that in Q-SYS is you are actually setting yourself up with a gain structure at clip, which will not work, and it will sound horrible the rest of the way through. So what you are actually trying to achieve is approximately negative 20 dB on that DBFS meter. That's your nominal gain as we go through. And you want to go through every input. Before you start processing and tuning and dialing a room, you want to go through every input and make sure that they are hitting at that negative 20 DBFS. If you've got pots and you've got VoIP and you've got line level and you've got Dante and any of those things you have coming in, you want to get those all leveled out at a negative 20 DBFS. This way, as you go through your processing and you work your way towards your output stage, you've got a nice clean signal coming all the way through. So let's talk about microphones. Microphones have their own noise floor because they are picking up ambient noise in the room. So same concept applies here. You want to add preamp gain until you get to negative 20 dBFS. And if you have a really high noise floor on a microphone, you really want to try to shoot for 15 dB above the noise floor. That's the AVIXA standard for speech intelligibility. So you are wanting to make sure, if you're trying to hit a negative 20 dBFS nominal level with a microphone, that means with nobody talking and you just turn on the microphone in the room, if you have a noise floor that's negative 35 or higher, then you're not going to be able to get your good intelligibility out of it. So you've got to be able to get that noise floor down before you bring it in. You've got to figure out how to quiet up that room a little bit, because we're not going to be able to get that much out of it once we get it into the system. So like we're saying in here, if the nominal level that we're shooting for is negative 20 dBFS and your noise floor is above negative 35, we cannot ensure our intelligibility. The easiest way to test this and check this is to have somebody start talking into the mic at their normal distance and level and whatnot. Adjust your preamp gain until you get to negative 20 dBFS. Have them stop talking and then just listen or just look at the meter with the mic just open. Again, negative 35 is that level that we're looking for. If it's dropping below negative 35, great. We've got a good SNR. We've got our 15 dB. We're ready to go. If it's above negative 35, then something needs to get addressed inside that room. There's just way too much ambient noise inside that room that needs to get dealt with, because we're not going to be able to fix that inside the DSP. All right, so here we are. We're still showing our, now we're looking at our noise floor being negative 42. That's giving us a nice 22 dB SNR. So this will look good. This will work. This will meet our standards for speech intelligibility. So now that we have our signal in, now that we have we've balanced and we've gotten ourselves a good strong signal coming in at the mic line input, let's look at what we're going to do once we get it inside. The three most common blocks that we use for this are high pass, low pass, parametric. This is, you will see this in 99.9% of systems on the input, especially on a microphone. The high pass is going to take out any of the low end rumble that you might catch out of the room. Generally you'll generally you'll find that somewhere between 60 and 80. If you're setting up a microphone for somebody that tends to have a lower voice, sometimes you may want to roll that up just a little bit. But as a general rule, somewhere 65, 75 in there is pretty good. You're also going to set up a low pass, which is going to trim off the highest frequencies. Start that around 16. You can back it down if you have to. And then when we get to your parametric, a lot of times the microphone manufacturers will have a recommended EQ curve, or they'll show you a plot of frequency response across the spectrum. And you can use that to flatten out any frequencies that might be just a little strong. Also, if you're having any feedback issues, you can go through and find those, and you can pull out those frequencies that are giving you any feedback. So that's what you would do inside that parametric. So like we said, you're going to consult the microphone manufacturer for your recommended curve. Use separate EQ components for your mic EQ and your room EQ. So we talk a lot about this if you've watched the dynamic audio processing class. We go into this a little bit where we talk about input processing versus output processing. I always recommend that you have a high pass, low pass, and a parametric for all of your inputs, just to kind of smooth those out, especially microphones. But you're also going to want to have a parametric EQ probably on the back end to deal with any room anomalies. Even if you're using Q-SYS speakers where we have the intrinsic correction blocks, you still probably want to put a little parametric in there, again, because the intrinsic correction blocks are just going to flatten out the speaker as a device, but they won't necessarily account for the room. So the other thing that you'll likely do on a microphone parametric is if you're having any speech intelligibility issues, then you may want to give a little bit of a spike to the 3 frequencies that we show in here: vowels, which are typically 250 to 1,000, consonants, which are 1.5 to 6K, and then your sibilants, STs and Zs, those are from 5 to 8K. So if you're finding yourself losing them, if the speech just sounds kind of muddy, then try to isolate whether it's a vowel or a consonants or sibilants, and then you can kind of tweak that up a little bit. All right, so if you are finding yourself having feedback frequencies or having feedback issues, then we do have a block that is a notch feedback controller. This will typically go after your high pass, low pass parametric, and it's a pretty simple block to use. You plop it in, set the fixed filter count to 0, give yourself a dynamic of 5, run it from 80 to 20, find the threshold of your feedback, turn it up just a little bit, and then start making some noise. And then what you will see is, like in this example right here, you'll notice that we're having feedback issues spike in from about 150 to 210, as well as we're having some issues up in that 600 to 800 range. And then from there, what you can do is you can go into your parametric, and this is why your high pass, low pass, and parametric will go before the notch feedback filter. So now that we know we're having issues in there, we're going to start with our lower frequencies. So we're going to put a band at 200 and a band at 700 and drop those down. And we're only going to pull out as much as we need to remove the feedback. You do not want to go crazy with this. If you start just having to pull a ton of frequencies out, you're going to kind of jack up what your signal sounds like. So you just want to take out as much as you need to get it to quit ringing. You'll do this one microphone at a time, making sure that you get everything out and then move again. we talk to people about taking out the NFC, the notch feedback controller after you're done with it, just because of the way it's processed in DSP. If you've got 20 microphones in there, you don't want to just have 20 notch feedback controllers that are just chewing up DSP space. If you feel like you need to keep one in, then what we recommend that you do is set up your signal chain and then put a notch feedback controller in there, and then use either a router and a probe or something to just route signals to it. And then you can use that anytime while you're live to spot check, or if you've got a frequency that pops up, you still have the block there available, but there's only one instead of having a whole bunch of them in there. Okay, now that we have processed our inputs, we have our inputs set, we've got a nice linear gain structure that's already set and ready to go. It's healthy, it sounds clean. Now we want to mix some signals together, and we want to start processing those as we get closer to our output. So we have two major mixer types. We have a matrix mixer, which is just a point-to-point. You assign what goes where. The output level is simply a matter of whatever's mixed to that output. If you are looking for something that doesn't need an operator, where microphones are getting mixed to an output, you will want to look into an auto mixer because the output level remains constant regardless of the number of open mics. If you've ever tried to run mics through a matrix mixer and you have 3 or 4 microphones that get open at the same time, you will notice that they just get really loud because you're essentially doubling the input that comes in as everybody opens a mic. So what you really want to do is run that through an auto mixer so that it will do its job, which is to, as mics get opened, it will keep that gain down to keep the room from just getting really loud and noisy. So let's go through our different kinds of mixers here. The matrix mixer is pretty simple. You pick the red mixer or the blue mixer, and that's how you get into a matrix mixer. Just kidding. Horrible joke. A matrix mixer. This is all pretty basic. What goes in, what comes out. You got a set number of inputs, set number of outputs. Assuming that they're all adjusted to nominal, you really shouldn't have to do much to your input and output levels. Cross-point mutes can be enabled to route or unroute without changing the gain. You will see this a lot in systems where you don't necessarily know what's going to go where at any given time, especially if you are heavy on line level signals. Lots of program material or input plates, things like that. You'll see that a lot for matrix mixers. Auto mixers. So we have 2 different kinds of auto mixers. We have a gating auto mixer and we have a gain sharing auto mixer. They do sort of different things, and we will cover them very briefly here. In this, what we're showing, this is a gating auto mixer. The most important thing, I think, is the max nom, which is max number of open mics. If it is an 8-channel auto mixer, do not have a nom of 8. Really never more than 3. The old joke is, one person talking is a presentation. 2 or 3 people talking is a discussion. 4 or more is an argument. So what you really want to do is you want to keep that max number of open mics down. Even if you have a whole bunch of them, keep that down, because what it's going to do is if you've got 10 mics in a room, 12 mics in a room, and you've got that nom set to 6 or 8, if that many people start talking at a time and they're getting above that threshold for whatever reason, you're going to start fighting giant feedback issues having that many mics open at the same time. So we've also got a last mic on. This will keep at least one mic open at any given time. In lieu of that, we also have a default button and a manual button. The default button is to say, if nobody is talking, open this particular mic. We also have manual buttons on there so that you can force a mic to be open. If you are using this with for processing room microphones for far end conferencing, we always recommend leaving the last mic on active so that at least one mic is open at any given point. Otherwise, your far end will just hear dead air. And well, it won't even be dead air. They'll just hear nothing. And it'll sound like the call has been cut off. So at least if you leave one mic open, they can at least hear that the room is on and they know that they're still there. So that's just a little side note. So the way the auto mixer works is if you've got 8 microphones in here and you've got a nom set to 1 or set to 4, if one person is talking, that mic just passes straight through. No attenuation, no nothing, just ready to go. When you get to 2 microphones, you now have a 3 dB attenuation, and that gets shown on the right-hand side under the gain. As you start to get into 4 microphones, now you've got 6 dB of attenuation. And again, this is just to keep the system from running away. So otherwise every time you opened more mics, it would just keep getting louder and louder and louder. And we want to maintain a constant level, especially if we're dealing with reinforcement and feedback issues and things like that. So this is why we also recommend that you have no more than 3 open mics at a time. So that is how the gating auto mixer works. The next one we have is a gain sharing auto mixer. So this is based on the Dan Dugan gain sharing algorithm, where the maximum gain is 0. You will notice there is no more number of open mics because in essence, every mic can be open at a time. You set an open indicator threshold and a depth and a rest gain and a minimum threshold, as well as some attack, hold, and release times. And what happens is every time another person starts talking and that mic triggers as open, it will pull down the gain of every mic in there. So with this one, we've got a set amount of gain across all of the inputs, and the microphones share that available gain. That is why it is called a gain sharing auto mixer. So as you can see, we've got 1 talker right now. The other 3 are considered closed, so they are all the way, they've got -30 gain being applied. As we start to get more talkers active, we start pulling more gain out of it. So you've got less gain per microphone. This works well if you only have a few microphones and you don't want to have to worry about nom or anything like that. If you start getting into 8 or more microphones, or if you're doing a scenario where you want to minimize the number of people that can talk at a time, then go back to the gating. Otherwise, the gain sharing can work. All right. So now that we've gone through our mixing, now we're going to do a little bit of output signal conditioning. Here is where we have a parametric on the output so that we can tweak for the room. We've also got an inline peak limiter for some output signal conditioning because we are just going to the line outputs on a core to some sort of an analog amplifier. So we're going to put a limiter in there to protect that output circuitry. You'll notice in this one, and this is fairly common, that you will see an auto mixer as well as a matrix mixer down or in line together. This is perfectly fine. We don't want to do a lot before an auto mixer, just because we don't want to make a lot of adjustments there. We want to have a pretty nominal signal going in before we start to hit that auto mixer, just to make sure that it's got enough information to make the decisions on, you know, is it open, is it closed, gating, gain sharing, things like that. But mixing them after the fact is perfectly reasonable, happens all the time. For those of you that have taken the dynamic audio processing class, you will be familiar with the compressors, limiters, gates, expanders, automatic gain control, things like that. Here we're looking at, on the input side of a microphone, we've got a compressor, which is a compressor will only let a certain signal come out. So if you get above a threshold on a compressor, it's going to bring down that level. This will help you level off people who are loud. If you're looking for spoken word, generally people are not a huge fan of compressors on people who are or who are speaking. This is very common if you're doing vocal performance, singing. But it will not do anything if somebody is quiet. Automatic gain control will help you bring up quiet talkers and bring down loud talkers. However, they are a little bit slower to use. They need a little bit more time to figure out and to calibrate. They definitely take more work to set up in a room, and you have to be very careful on setting up your thresholds and your maximum gains, because you can really get yourself into trouble where you end up turning up a microphone signal to the point where it starts ringing in the room. If you haven't taken the dynamic audio class, I highly recommend it. It goes into some details and actually shows what goes on inside the blocks of compressors and limiters and expanders and gates and the AGC, and gives some really good best practices for how to dial that in. Okay, so what's wrong with this picture? Never put a gate in front of an auto mixer. We see this a lot when people have bad SNR. When people are having a lot of noise come in, they try to gate a mic before it hits a mixer. The only problem is, first of all, you're not going to solve the problem that way. You still have a bad SNR. You still have a noise floor that's way too high. So this is not solving that problem. And second of all, you are completely defeating the purpose of that gating auto mic mixer. It's just not going to work right. It's going to get weird signal. It's not going to know whether that mic really is open or not. This is just going to cause you massive issues. Okay, now that we have gone through our gain structure and we have set all of that up, let's take a few minutes to go through AEC and talk about acoustic echo cancellation. This is specifically for conferencing applications. This is making sure that when the far end speaks and the far end material comes out of the speakers in the near end, that's the room that you're in, that speech does not come back into the microphone and then travel back to the far end. That's the echo. I'm sure everybody has heard it at some point in their lives. So let's talk about a couple of things when we get into AEC. First of all, it takes a while to get that signal removed. So the algorithm needs to be able to look ahead. Our older algorithm took about 13 milliseconds. Our newer one that's in the 110 and the 8 flex and the nano takes about 21 milliseconds. All of the other cores that are running firmware 6.0 and higher take about 10 milliseconds. You'll see us talk about tail length. This is how long the algorithm looks for echo before it gives up and releases the reference. We have 100, 200, 300, and 400 millisecond options in Q-SYS. The default is at 200. When we talk about number of AEC channels available onto a core, this is all based at 200. I will tell you right now, it is a bad idea, and you will find yourself in trouble if you start trying to design around a 100 millisecond tail length thinking that you can eke out some more. Because if you try to eke out more channels and you get in the room, and wow, this room is actually a little bouncier than I thought, you will find yourself in trouble because you can't turn that back up without going over resource allocation with your AEC. It is rare that you have to wind up to 300 or 400 milliseconds. If you are in a room that has marble floors and glass walls and a hard lid ceiling and a marble table, just don't do it, because you're going to have to pull that tail length out, and you're going to fight every reflection in that room. So let's go through some other things that we're going to talk about. RMLR, this is a big one that we look for. This is the difference in the level between the reference signal that you're feeding into the algorithm and what the mic actually is hearing out of the loudspeaker. So we always talk about this as loss, because the reference level should be nice and big and strong, and then the level that the mic actually receives should be lower. So what we're looking for is that difference. So this is also called ERL. You'll see a lot of people call this echo return loss. That's how much signal gets lost as it bounces around the room before it comes into the room, or before it gets picked up by the microphone. So we will talk about, you'll see some reference to residual echo suppression. This is the same as our nonlinear processing. This will help. You can turn this up a little bit if you're still getting some error signals after the AEC. We also have voice lift outputs on our AEC block. If you're in a large room where your near end microphones are getting sent to the speakers in the near end, then that's called voice lift. You'll also see us talk about mix minus. If you're in a big room where you are using voice lift for speakers and your microphones are fixed in spots, generally what you will do is, if I'm sitting here talking into microphone 1, I don't want microphone 1 to come out of the speakers that are right up above me. I want them to come out really strong in the speakers that are farthest away from me, and then progressively quieter as I get back towards myself. This can be tedious to set up, but when done properly, a minus mixed room sounds beautiful. It sounds very natural, because the closer you are to the actual speaker, the more of their natural voice you'll hear. And then the farther away, the more you'll hear it out of the reinforcement. It can be, like I said, when done properly, it's a great sound. So we've talked about near end. So near end is the room that you're in. Far end is the people that you are conferencing with. It does not have to do with the near end of the room and the far end of the room. These are two different places. So our path to the far end, we will have some local microphones. Those will get run through our AEC block. They will then go to an auto mixer, which will then feed our VoIP output, which is what the far end is going to hear. For our near end, we're going to have some program sources that we're going to hear. And we are also going to have the far end, because we want to hear them in our speakers in the room. So we're going to mix together our program sources and our far end, and then we're going to send that out to our speakers in the room, which also becomes our reference. So we are also looking at a way to, or we're also looking at processing our microphones. The best practice is to do any of this after the AEC algorithm, mainly because you want the AEC to hear as clean a signal as possible. And if you've got any dynamic audio processing, a compressor, an AGC, anything like that, that needs to be after the AEC, because we want the signal going into the AEC to be as steady as possible. We don't want something that's going to make that gain jump around as we're trying to cancel out that echo coming back through. So never, ever, ever, ever put a dynamic ahead of an AEC. So let's talk about creating our reference. Creating a strong reference is critical for this. It is what we see time and time again between support and the app engineers. When people call us and they say, this room just sounds awful. I cannot get it to balance out. My far end says it sounds awful. Most of your systems that you're going to deal with, your small to medium sized conference rooms, your huddle spaces, anything like that, you will not be using voice lift. So what we generally say is whatever goes to the speakers goes to the reference. So that's all of your far ends. If you've got multiple, if you've got VoIP and POTS and USB from an MTR or whatever it is that you've got going on, make sure they all get sent. Program sources, especially if they're going to the far end as well. But you never want to put a mic into its own reference. If you've ever heard somebody say that it sounds like they're underwater, it's because the mic has been sent to its own reference and it's trying to cancel itself out. So bad juju. Assuming that we've already got our mic signals set properly and that we've got our 15 dB of speech intelligibility, so we're going to set our amplifiers to their minimum level, or we're going to set our output blocks to -40. We're going to use our preamp analog to bring all of our program sources in at -20. This is all about our gain structure that we said earlier. And then we're slowly going to bring up our amplifier or our line output until we get to a comfortable listening level. Once we have a comfortable level set, then we're going to adjust our far end gain to make sure that we are putting out a nice clean -20, which is our nominal that we're looking for. And then once we have a listener on the far end and we do some test calls, then we can fine tune the AEC. So what we're going to look at is a couple of things. First of all, if you're going to turn on the noise reduction, this is only going to look for steady state noise. So this is your air conditioner or maybe an elevator or something like that. It's not magic. And the more you put in, the more it's going to start to color your microphone signal. So be very careful with how much you put in. The next thing that we're going to look at is our RMLR. So we're looking for a target of 0. So we're trying to get to a point where we have a signal that is at least at the same level of what the microphone is picking up. So you can adjust that reference gain if you need to. You can turn that up or down. You don't want it too high because you don't want to overdrive that. And then if it's too low, it'll have a hard time pulling it out. You'll still get little bits of echo, especially early when the person starts talking. So you want to make sure that you have this on. You can use the adaptive filter. That's if you can't mute the mic after the AEC. You can leave it at a -100 if you're muting it post AEC, but if you need to set the adaptive filter to overcome some kind of a noise floor, if you've got a noise floor of -60, then you can set your adaptive filter to -65 or something like that. So Oh yeah, here we go. Now we're talking about adaptive filter. So that's where you would set that. Most of the time, you're just going to leave that at negative 100. So if you are still getting echo after you have set up your AEC, you can enable your RES and turn that up, but be very careful because the closer you get to 100%, the more you're going to get the half duplex, meaning that only one person can talk at a time. So if you've got double talk, or you need to be able to have a full duplex conversation where if your far end is talking and you talk at the same time, then you need to be able to get to that point. But if you start talking while they're talking and then all of a sudden they start to hear echo, then go ahead and turn up that RES until there's no echo that's heard, but where they can still hear you. So what if you still have a bunch of echo? If you still have a bunch of echo, then make sure that all your signals are right. You don't have anything looped. If you've got video codecs, that can happen pretty easily. Go ahead and mute the microphones and make sure that you've actually got echo and not coupling, which is sending the same mic into the same chain at the same time. And then if you still have echo, then start muting inputs until you can figure out which source might be misrouted or might be set up poorly. If you've still got a bunch of echo, then if you're at 100 milliseconds, you can go to 2. If you're at 2, going to 3 or 4 might not fix it. Otherwise, you really want to look at treating the room instead of trying to fix it in the AEC. So the last thing we want to tell you is always make sure that you repeat a test call for every conferencing type. If you've got VoIP and POTS and some sort of a USB BYOD or whatever it is, run through each conferencing type individually to make sure that you're not getting echo on any of them. So that's something that's really important. So after we've gotten our mix together, now we're going to look at some output EQs and limiters and things like that. So we're going to put an EQ on the speaker side to help flatten out individual speakers. Typically, the speaker manufacturer will give you some sort of a frequency response across the spectrum. You can use that to smooth out high and low points. Again, if you are blessed enough to be using QSC speakers and QSC digital amplifiers, then you can just drag in the blocks, and that is intrinsic correction, and that is built into our amplifiers and our speakers. Even if you are not using our amplifiers and you are just using our speakers, you can bring in the block and have it pass through to a line output, and you will still get the intrinsic correction for our block or for our speakers. That's shown over here on the right-hand side. You'll notice that we've got some ADS-12s that we're running inline, and we are feeding those to the line out on an amplifier. The fourth channel is clearly some inferior non-QSC speakers, so we have to put just a regular parametric on there and try to set them up. When we talk about putting user gains, some people will, or some applications will require the actual inputs to be level adjusted. We see that a lot in conferencing where people want to control the program material versus the microphone levels. If you're doing more like hospitality or, other sort of events where the inputs are fairly fixed and you just want to control the room, then you would want to put it at the end. Try not to do both, and certainly don't give the user both. They do not need to be adjusting inputs and output side gain structure at the same time. And remember the rule, if you're doing conferencing, only give people control of a signal they can hear. So don't it is generally not best practice to give people control of the level going to the far end. You can't hear that. You don't need to adjust that. If you have done your job and everything is set and you have a nice nominal negative 20 DBFS at your output, then that's on your far end to make sure that their signal is getting processed properly. If you start cranking that up, you can start really throwing off their AEC. You can start just giving them a bad signal. So just not a good idea. So just be very careful with the gain controls you put in, and then especially with the ones that you give users the access to. And always remember that you can set upper and lower limits on your gains. So I highly recommend doing that. We've got some limiters on the output. This keeps a signal from going beyond a predetermined level. We go over a bunch of limiting in the dynamic audio class. Typically, it comes in with a default threshold at 0. We usually show, because even at a 0 dB threshold, because there is a 10 milliseconds that it takes to attack, a signal can get in above that. So that's why we will typically recommend coming through and setting your limiter at -3. Setting it at 0 cuts it a little close. If you reduce that by 3, then you have a little bit of margin of error before the clip actually happens to catch the signal and pull it back down. Our amplifiers have limiters built in. If you're using our speaker blocks, those communicate with each other and they build in limiting. So you do not need to put in output stage EQ or output stage limiting just for the speaker. You may still want to put EQ in for the room, but you wouldn't need it for the speaker. So if you're not going directly to a Q-SYS amplifier, then we have to get the digital audio from inside the DSP back to analog to feed an amplifier. In the limiting example, you saw that we set the clip at at 0 DBFS. So keeping with our ideal structure and our -20 DBFS, our digital gain should be left at 0, assuming that we're nominal all the way through. At our 0 dB digital gain, then our analog output, which is going to be our max RMS output out, is going to come in at 0. So this is perfect for our professional downstream device where we want a +4 nominal and a 24 dB max. So what do we do if our next device is a consumer line level device? So ideally, we want everything to clip at the same point. So if our consumer line level is at -8, and we want to keep our 12 dB headroom, which means we have a maximum input level of a +4 dBu. So what we want to do is we want to turn that output gain down so that we can not hit that input side of the consumer device too hot. Okay, sometimes you have to feed a microphone level device. So the first thing you want to do is make sure that that device is not putting out phantom power, because the output circuitry is not designed for that. And then in this case, you want to cut your max RMS output level to -40. So you can see that our output gain is turned all the way down to -61. And at this point, you should be getting an actual analog output that is roughly mic level. You may have to play with that just because mic levels are not standardized. So as we look at our output gain structure, decreasing our output level decreases our SNR. So you really want to use professional line level equipment where possible. That gives you that maximum SNR and that maximum dynamic range that you have to play with. So in review, input calibration. We want all of our analog gains at negative 20 DBFS. Negative 20 DBFS. I'll say it again, negative 20 DBFS. That is our nominal input as we work our way through our digital space. All of our inputs, microphone, program, conferencing, all of it needs to get calibrated to be at the same level. Mics, we want to trim our high and our low with some high pass and low pass filters, parametric to flatten it out. A notch filter or our parametric can also be used to trim out some feedback frequencies. And once you're done with your notch feedback filters, don't forget to take those out so you're not chewing up unnecessary DSP. Microphone dynamics. AGCs and compressors can be used to get consistent levels from wider ranges of talkers. Auto mixers, don't give user level controls or gates ahead of the auto mixer. You want that to get a nice clean signal. Use gating auto mixers for noisy rooms, or if you've got a bunch of mics, use gain sharing auto mixers, or you can use gain sharing auto mixers for smaller rooms. One of the biggest things is just use the fewest user gain controls possible to get the job done. You want to avoid multiple controls in the same signal path. You also want to adjust ranges to avoid letting users ruin your gain structure. You spend a lot of time setting this up. Don't let your users jack this up for you. Output limiting. QSC amplifier limiting applies automatically when you use intrinsic correction. You can use a peak limiter component to protect your outputs. Make sure you set them to -3 DBFS, assuming you have proper nominal structure throughout. And then you can use your analog output gain to adjust your max output level to the clipping point of the next device in line. So last thing, if you go to qsc.com/gain structure, there is a short little quiz, and this class is worth a half of an Avixa RU. This says, don't forget to take a troubleshooting guide. This troubleshooting guide will be sent out along with the video. So you'll get this in a PDF, which goes through a sort of a step-by-step of how to make sure you set up your gain structure. Okay, here we are. Look at that, right at 60 minutes, which for any of you that have taken classes that I've led know that that is a minor miracle in and of itself. I know that I kind of had to quickly bang through this one. This has a lot of information in it. So at this point, if anybody has any questions, hit me. God, I feel like I've been talking for an hour solid. Just hear my own voice ringing in my head. All right, well, everybody have fun. Have a great day. Hopefully your weather is nicer than it is here. I live in beautiful South Texas where it will be 95 degrees and 95% humidity. Let's see. Mark is asking if I can go over AEC settings again. I'm not quite sure which settings you're talking about, but I assume you're talking about the controls. So let me find that right quick. Let's go like this. RMLR and RES. Okay. Let's see. Okay. Sharing. Okay. So RMLR is this little meter down here. It's circled. What you're going to be looking for is when your far end talks. So you'll need to have somebody on the far end talking for you, and you be quiet in the room. And what you're looking for is you're trying to make sure that when the microphone picks up whatever's coming out of the speaker, that the reference signal that you have already set up is higher than what it's picking up out of the microphone. So you don't want it crazy high. You don't want it like 20 dB higher. But the biggest thing is you don't want it to be in the red. So if your RMLR is too low, then you will, and your reference gain on this AEC block is already set at 0. You need to find where you are generating your reference. Well, there's a couple of things going on. You need to find where your far end comes in and make sure that you are set nominally from the very beginning, and then track that all the way through and make sure that it's not getting brought down anywhere, because that should be a nice strong 0 in, and then whatever you're getting past it or whatever you're getting in a reflection should be lower. So you just want to look at that. Now, if it's coming in and you're looking at that RMLR and it's like 12 or 14 or something like that, you can take that reference gain and pull it down a little bit and get it to where you're floating right around 0 or +1 or +2. I mean, it's obviously going to bounce around. You just want to make sure that it's not dropping below 0, because the algorithm is going to have a really hard time finding something or figuring out what to cancel if what it's picking up out of the mic is coming in hotter than what you're sending it as a reference to be looking for. Okay. So now that we've talked about RMLR, let's talk about the RES. So this is after it's been processed and you're still getting a little bit of residual echo, then you can turn up that RES. Generally, what you'll find from this is this happens in double talk, which is when the near end and far end talk at the same time. It's harder for the algorithm to figure out what to cancel out. And so you'll get a real quick echo. The far end will hear it. And that's where you want to turn up that RES. Again, you just want to be careful on that RES, because as you turn that farther and farther up, what's happening is the algorithm is going to prevent both sides from being heard at the same time. That's how it goes through and gets rid of that double talk condition, is by turning it into a half duplex, which if you remember, or if you are old enough to remember setting things up like modems and things like that, you know, half duplex, basically communication can only travel one direction at a time. Full duplex communication can travel both directions at the same time. You want full duplex communication when you're talking about conferencing. You need to be able to interrupt somebody and say, whoa, hold on, or they can interrupt you, whatever it is. If you're in a half duplex situation, if one person's talking, they basically control that conversation. So that's where RES figures out. RES is after you've set everything and you're in your test call. Did that get it? You mentioned the AEC reference in a room with no voice lift. What do you do for a room with voice lift? So if you have a room with voice lift, there are voice lift outputs on the AEC block that you can use to feed the room. But doing a room with voice lift can be a little tricky. It really has to do with you have to be very careful with how you set your reference, because you need to make sure that while your mics are passing to the voice lift speakers, you just have to be very careful that you're not getting your mics into your reference mix so that it is still just looking for that far end. The only reason voice lift makes things a little bit more complicated is because there's more noise potentially going on that the block has to try to filter out. So I don't actually have any slides that show doing it with voice lift, but there's a voice lift option that you can turn on in the block. And that gives you microphone outputs that are before the AEC processing that you can then feed and mix. That you can then mix to feed your voice lift. All right. Any other questions? Well, all right. I appreciate everybody's time today. We went over by about 10 minutes, but that's okay. Just a reminder, next Tuesday, we will be doing a whole class on the power of the Core Nano. I'm sure everybody is aware with supply chain and whatnot that's going on. The Nano has become our go-to processor. So we will show you all the things that a Nano can do, some of which you may not have even thought about being able to do with a Nano. The processor that sits inside of a Nano is incredibly powerful. It can do way more than you may give it credit for. Don't overlook the size of the box, or don't let the size of the box fool you. It is the Yoda of processors. And then tomorrow, Activate. Come hear from our product managers as well as some of our product specialists. This Activate will actually feature breakout rooms after the initial presentation, where we will have product managers and product specialists in different breakout rooms to answer specific questions about particular products. So come check that out. I believe the times, if you haven't already registered, go to Q-SYS.com. It's the first thing you'll see when you land on the homepage. And you can come see everything that we are working on over here at Q-SYS. I believe the times are 9 a.m. Central, 1 p.m. Central, and 9 p.m. Central. I am Central. That is how I base my world. Feel free to do your own math from there. And yeah, so Activate tomorrow, next week, Core Nano. I hope everybody has a great day. Have a great rest of your week. Stay cool if you are somewhere that it is still hot. Stay warm if it's already cold where you are. And I look forward to seeing all of you tomorrow at Activate. Have a great day, everybody. Bye-bye.